Top of the morning to you. And a happy St. Patrick's Day. For our first remote learning, thought we might start with a pun. So why do people wear shamrocks on St. Patrick's Day? Apparently regular rocks are too heavy. So there you go. I know you guys are wishing I would try to stick with my fake St. Patrick's Day accent for the entire first remote learning lesson, but I'll let it go right there. And instead, we're going to just write in green today. I hope you're wearing green right now. I'm recording this on St. Patrick's Day morning here. So here we go. Well, where we left off, we were looking at our similarity shortcuts for triangles. And today we're going to be talking about how parallel lines in a triangle produce proportional parts. So when a triangle contains a line that is parallel to one of its sides, the two triangles can be proved to be similar using, if you recall, the angle-angle similarity shortcut. Okay, so recall when we have parallel lines, that produces corresponding angles that are congruent. It produces alternate interior angles are congruent. So we end up with angles that are congruent, and if we have two angles that are congruent, then we know that the triangles are similar, and therefore their sides are proportional. That's the definition of similarity, when you have congruent angles and sides that are proportional. So we look at how this works, triangle proportionality theorem. If a line is parallel to one side of a triangle and intersects the other two sides, then it divides the sides into segments of proportional length. So let's look at this example over here. So we're saying, if you see this, notice we have our parallel line markings here, parallel segments. And if we see that, we divide this segment into two parts, and those two parts are going to be proportional. So let's say AB is 6, then BC is 2. And so that is a 3-to-1 ratio. So what that means is that on our other sides, that we're going to have that same proportionality. So let's say AE is 9. That would mean that ED would be 3. So that 3-to-1 ratio there would hold for those two sides that are being intersected. Okay, so let's just do another example here. In triangle PQR, if ST is parallel to RQ, and if PT is 7.5 and TQ is 3, and SR is 2.5, find PS. So let's write all of those in. See how this works here. So PT is 7.5, TQ is 3, SR is 2.5, and find PS. So we're looking for this length right here. All right, so we'll notice that we have the parallel lines. So what we're going to have is proportional parts on both sides. So we can set this up and say, okay, that means that the ratio of, say, 7.5 divided by 3 is going to be the same as the ratio on the other side of the triangle, so x over 2.5. All right, now I do like to use the cross multiply and divide method for solving my proportions. So we're going to do that here. And so we have 7.5 times 2.5 is equal to 3 times x. If you break out the calculator, 7.5 times 2.5 will be 18.75. It's equal to 3x. And then dividing by 3, we get x is equal to 6.25. So let's just look at what that actually means. So this is 6.25, and we're trying to find PS, which is the 6.25. So PS is equal to 6.25. So like all of the problems we have done in this unit, really, or almost all of them, we are solving a proportion. So it's just a matter of figuring out how to set up the proportion. So the converse of this is also true. Recall, we've talked about converses throughout the year, and basically our conditional statements for our theorems are typically in an if-then format. That is what a conditional statement is. So the converse would flip the if and then parts and see if that is also true. And in this case it is. If a line intersects two sides of a triangle and separates the sides into proportional parts, all right, so proportional corresponding segments. So if we start out with a proportionality, then the lines will be parallel. Then the line is parallel to the third side. So once again, we think of this as the if part. So if we actually know the ratio here, if we see that these two sides are proportional in a 1:5 ratio here, or 5:1, depending on which direction you're going, then we can say that these segments would have to be parallel to each other. So notice we start off with the proportionality that we notice, and then we finish with the parallel. So let's take that converse of the triangle proportionality theorem and apply it down below. So we're going to determine if DE is parallel to GH. So let's go ahead and see. So we're given some length relationships here. We have EH is 3 and we have HF is 9. And then we're told something a little bit different here. We're told that DG is 1/3 of the length of GF. Okay, so we don't actually know those segment lengths. We just know that they are in relationship there of 3:1. So that in itself essentially tells us what we have here, that we do have a 3:1 ratio between the two sides. Even if we don't know the length of DG and FG directly, we do know that the ratio is a 3:1 ratio, and that is true for FH versus HE. So yes, since 9/3 is equal to 3x over x, in other words, if we cancel these out, we see that we have a 3:1 ratio over here, over on this side. Then DE is parallel to GH.